So now we come to a type of solution concentration called molarity. And this is the one that chemists use the most. Because what did we always have to convert to when we were doing stoichiometry? We went from grams to moles, right? Because moles are reflective of the number of particles. And when we think about chemicals reacting and molecules reacting, it's the number of particles that's important. And so mole is just our giant chemist dozen that helps us count molecules. So a percent composition, like we looked at on Monday, is useful for many things, but when we need to know how many moles of something there are, a concentration that uses moles is much better. So chemists use molarity. The abbreviation for molarity is a capital M. Now, capital M's and lowercase m's often look a lot alike. So this, whoops, that's not even a very good M. Is that a capital M or a lowercase m? Hard to tell, right? Oh, no, it's a capital M. It's hard to tell. And so, unless you're going to be very careful and make your capital M's pointy and large and your lowercase m's curvy and small, most of us don't have time for that. So the kind of understood thing that chemists do is we underline our capital M's. So if you see me doing that, that's what I mean. When you type it, it's more obvious. When you're just doing it handwriting, I underline the capital M, just to say this is a capital M. So molarity means moles of the solute, that's the thing that there's less of, per volume of solution in liters. Okay? So it's moles per liter. So here's another way to look at that. Capital M stands for molarity, which means moles of solute per liter of solution. Not liter of solvent, but liter of the whole solution. So if we see something like this, and you've seen this letter on the reagent bottles in lab, haven't you? And some of you have asked, why does it say 3M on there, you know? What, did 3M manufacture this? That's a company, 3M. No, it's a concentration unit. So 3 capital M HCl means there are 3 moles per liter of solution. That could have been made by putting 6 moles of HCl in 2 liters of solution. And when you do the math on that, it comes out to be 3, and then the units would be moles over liters, or we abbreviate that 3 capital M. And this is a really useful unit because we can take a solution, and liquids are tricky to weigh on a balance because you don't want to spill them on the balance and you have to hold them in a beaker and you have to mess around with them. Using a concentration like this, we can measure the volume in a graduated cylinder and know how many moles we're adding to our reaction. And so it's a really useful unit for chemistry. So let's do some examples and learn how to work with molarity. So let's say we have 1 mole of sugar in 125.0 milliliters of solution. Calculate the concentration in units of molarity. I will give you that equation, this guy right here. Oops. Enter drawing mode, this guy. I will give you this equation on your page of useful information. So when we do a question like this, it wants the molarity, so then we remember or look up that molarity equals moles per liter. And I warned you and did an example where questions try to trick you with the percent composition by telling you the mass of the solute and the mass of the solvent, and then you have to actually do a little math and add them together to find the mass of the solution. They don't try to trick you in questions with molarity because it's too hard. If you've got a mole of sugar, and if we gave you the volume of the solvent, there's no way to predict what the volume of the solution is. So you'll see when we talk about how we would make up these solutions, they're always going to give you the volume of the solution, which is what we need. They will sometimes, though, do this, where they'll give you milliliters instead of liters. And it's important to remember this is moles per liter. So here we have moles of sugar, but we've got the volume in milliliters, so we need to convert that. So let's convert 125.0 milliliters. We need to change that into liters, which means we multiply by liters and divide by milliliters. What does milli mean? 10 to the what? -3. So up here I'm going to write 10 to the -3. And we look at our units. Milliliters cancel milliliters. And we end up with 0.1250 liters. Doing that on your calculator, 10 to the -3, it's best to just use scientific notation. That's the same as 1 times 10 to the -3. So 1 EE minus 3 times the 125. If you've gotten comfortable with conversions like this, going from milliliters to liters, all you have to do is take this decimal point and move it over 3 places. So that method works for some people and not for others, and that's why I'm always going to write these out. It's for those that don't like the moving it over. Because some people have a hard time remembering which direction am I supposed to move it. So here we've got our volume, and now we can say molarity is the moles, so 1.00 moles of the sugar, divided by the volume of solution, I always forget to get my calculator out. So 1 divided by 0.125, that equals 8. The calculator is showing me 8. How many significant figures should I report there? How many are in this number, 1.00? Take a guess. Those pesky zeros, are those significant or not? There's a decimal point there at the end. So this one has 3 significant figures. We're going to count those zeros. And this guy in the bottom, he's got zeros at each end. This 0 is just to call attention to the decimal point. Zeros at the beginning of the number never count. And this 0 at the end, there's a decimal point in the number, so this one does count. So this number has 4 sig figs. 4 versus 3, 3 is a smaller number. So we need to put 2 more significant figures on our number 8. Well, what are the next digits? The calculator's not showing them. They would be zeros, right? So it's going to be 8.00 moles per liter. So you can write it that way, or you can say 8.00 capital M. And when we read a concentration like that, we say 8 molar. So this is an 8 molar sugar solution. Any questions? This is a more practical solution, a practical problem. Hopefully the solution will be practical too. A 500.0 gram sample of potassium phosphate is dissolved in enough water to make 1.50 liters of solution. What is the molarity of the solution? So this one's more complicated. They're not giving us a number of moles, are they? They're giving us a mass and a name. They are giving us a volume of solution. So we read through a question like this, and we see that they're asking us to calculate the molarity. We're going to use that molarity equation. So it's helpful to write that down. So molarity equals moles per liter. And usually that's enough to help us remember what we're supposed to do. We find the number of moles of the solute, the thing that's dissolved, and we divide it by the liters of solution. Well, here's liters of solution, but they didn't give us the number of moles of potassium phosphate. And this problem is more difficult than what I would give you on an exam because they're not giving you the formula, they're giving you the name. But it's a good review for us. So potassium phosphate, we need the formula of that, because what we have here is we have 500, that's not 500, 500.0 grams, and we need to convert that to moles. Can we convert grams of a substance to moles? Yes, we can. What do we need to use for the conversion factor? The molar mass, right? We need the molar mass. So converting, we're going to put a conversion factor in here. We'll have moles on the top and grams on the bottom, and we'll end up with moles. We need to find the molar mass. To find the molar mass, we need the formula. So if this was an exam question, I would give you the formula. Because on the final, I'll ask you other questions where I'll give you a name and ask you to write the formula, but I won't combine them together. They'll do that in 3A or Chem 1A, but not in Chem 10. So we need the formula for that. Potassium phosphate. What's the element symbol for potassium? K. Is that a metal or a nonmetal? It's a metal, right? It's over here on the left side. So is this compound an ionic compound? If it's got a metal in it? Yes, it is. All compounds in this class that have metals in them are ionic. So then we have to deal with charges. So what's the charge on the potassium ion? 1, right? It's in group 1, so potassium always forms a +1 charge. Phosphate. Are we going to find that directly on the periodic table? No. It's related to phosphorus, but it's one of those polyatomic ions. And if you need to do this on an exam, I'll give you the chart. So let's pretend we go look it up in the chart, and we see that phosphate is PO4, 3-. We need those formulas of the ions so that we can figure out what the formula for the compound is. And we need the charges. So here are the two ions. This is potassium and phosphate, and we just have to figure out what ratio they are put together in so that their charges cancel each other out, or they add up to 0. So here we've got -3, and here we've got +1. So if we had 3 of the potassiums, that would balance the charge on the phosphate. And so the formula is K3PO4. The other way we did that is by doing the crisscross thing. And you get the same answer that way. Now that we have the formula, we can calculate the molar mass. I'm writing far too big today. Must be the ice cream. So, well, let's sneak it in here. So we've got 3 potassiums, and those are what, 39.10. And how many phosphorus atoms? Just 1. And so we look up its molar mass, and it's 30.97. And how many oxygens? 4. So we have 4 times the mass of oxygen. And we put that all together. 3 times 39.10 plus 30.97 plus 4 times 16, 212.27. Hmm. 27 grams is equal to 1 mole. Oh, good grief. Okay. There we go. So this number is what we put in here. We've got 1 mole weighs 212.27 grams. So this enables us to find how many moles 500 grams is. So we've got 500 divided by 212.27. And that's going to be 2.355 moles of potassium phosphate. So all this stuff that I did down here is stuff we've learned in previous chapters. And, you know, it's some of these things that we keep using over and over again. Now we have what we need. Here we have the moles of the solute and the liters of the solution. And so we can take these and plug them into our equation. We've got 2.355 moles divided by 1.50 liters. So we end up with 1.57 capital M. It got kind of squished over there. Capital M is exactly the same as moles per liter. So you can write either one. Any questions? It's all the noisy people that aren't here today. Let's do another one. You have look at this, 10.0 capital M. If we're going to read this, we say 10 molar sugar solution. 10 molar means that there are 10 moles per liter of solution. What volume of the solution do you need so that you would have 2 moles of sugar? These can be done using the equation for molarity, but I think it's much better to use dimensional analysis. Because we take this concentration, 10.0 capital M, that is the same as 10.0 moles per liter. Does that look like a conversion factor? It does. That concentration, molarity, allows us to convert between moles of solute and liters of solution. If we have one, we can find the other. In this question, they're giving us moles of solute, and they're asking us for a volume of solution. This is our conversion factor that's going to allow us to convert from one thing to another. And I think it's better to think of it that way instead of taking and writing the equation down and rearranging it and plugging numbers in and solving. Because anytime we involve algebra, funny things sometimes happen, right? I think a lot of you have kind of a sketchy relationship with algebra. And that's okay. It's okay. So let's just avoid it whenever we can, right? If we're not super good at something and we have a different way to do it, let's do the other way that works better. So in this question, we can treat this as a dimensional analysis problem. Here we have this 10 molar. What's really important is that you write it down this way, moles per liter. So it'll give it to you with the capital M, write it down as a vertical fraction, moles per liter. The other number we have here is the 2.00 moles. And back when we were just doing dimensional analysis and learning how to take these word problems and find answers out of them, we would look at the numbers that were given and ask ourselves, which one looks like a conversion factor? Well, this one looks like a conversion factor because it has 2 units, something per something. And then we have this other one that's a single unit. Because the thing is, we have to decide which of these numbers do we start with? Which do we put first, and then which one do we use as a conversion factor? So this one with the single unit goes first. And then we're going to multiply. We want to find a volume. So liters would be a fine unit. And we're going to divide by moles. Just making the units work out. We want to find a volume, so we'll multiply by liters. We want to get rid of the moles, so we'll divide by moles. This has liters and moles, and so does this. This is the conversion factor we need. 10 moles per 1 liter. So 10 goes with moles, so we're going to put 10 on the bottom. 10 moles per 1 liter. Sometimes you multiply by the molarity, sometimes you divide by the molarity. The units will tell you what to do. Put the units in first, and then stick the number in. So this ends up with being 2 divided by 10, which I believe will come out to 0.200 liters. Let me double check that. Because, I don't know, my brain has been kind of on the fritz lately, so I don't really trust it anymore. Any questions? Yes? If you wanted to do that with algebra, you would use the molarity equals moles divided by liters. And then you would rearrange the equation, and you would end up with liters equals moles divided by the concentration. And so I'll just continue it. Yeah, there's no room up there. I'll continue it right here. So the liters would equal, I need to finish that. Moles over molarity. So I would take the moles, which is 2.00 moles, and I would divide by 10 moles per liter. The moles would cancel out, and I would get exactly the same answer. So that's a very valid approach, and if that makes sense to you, you go right ahead and use it. I'm going to stick with the dimensional analysis approach because I want to be consistent and show you the same way every time. Any other questions? Today's lecture is most about working problems. So here's another one. Consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each solute in 250.0 milliliters of solution. Calculate the concentration of each solution in units of molarity. So this one is more complicated than the last one, isn't it? Sometimes it helps to draw a picture. So I'm going to draw a picture. This is saying we have 2 solutions. So I'm going to draw 2 beakers. And one of the beakers has sodium hydroxide in it. And one of the beakers has potassium chloride solution in it. And it says it's made by dissolving 100 grams of each. So this beaker over here has 100 grams of sodium hydroxide. So it's got 100 grams of sodium hydroxide in that beaker. And there's 100 grams of potassium chloride in this beaker. And the volume of each of them is 250 milliliters. So they're giving a mass of a solute and the volume of solution in milliliters. And they want the molarity. So molarity equals moles per liter. They gave us grams and milliliters. How thoughtful. This is usually what happens, though, because we measure things on the balance in grams, right? And yes, we have to do a little calculating when we make the solution. Once the solution's made, a lot of these solutions can sit on the shelf in the stockroom for months or even years. And then if we need to get a certain number of moles, all we have to do is measure it in a graduated cylinder, and it's much easier than weighing things out. But initially, there's some calculating that needs to happen. So we need to find how many moles of KCl and how many liters of solution so that we can find the molarity, right? Well, the volume of solution is the same for both of them. So we could convert that. 250 milliliters times, we want milliliters on the bottom and liters on top. And then we say to ourselves, what does milli mean? It's 10 to the minus 3. So that's 1 times 10 to the minus 3. Milliliters cancel out. This is 0.2500 liters. So that's the volume. That's the part that's going in the denominator. Now we need to find the number of moles. Let's do this one first. Let's do the sodium hydroxide first. So we have 100 grams of sodium hydroxide. And we need to figure out how many moles of that we have. So we're going to multiply by moles and divide by grams. All right, this is just using molar masses to convert. Well, how do we figure out what the molar mass of sodium hydroxide is? We use the formula in the periodic table, right? So sodium is 22.99 and oxygen is 16.00 and hydrogen is 1.008. I think that adds up to 40. 22.99 plus 16 plus 1.008. Yeah, 39.998, which we would round to 40.00. 40.00 grams. So now we can take 100 grams and divide by 40 and find that this is equal to 2.5 moles. Of sodium hydroxide. So then the molarity of that solution equals the moles over the liters. So we've got the 2.500 moles. You know, I'm going to do this in a different color because it's all getting jumbled up together. So the molarity is going to equal the number of moles, 2.500 moles, divided by the volume, which was 0.2500 liters. So that comes out to 0.1000 moles per liter, which is the same as 0.1000 capital M. So the sodium hydroxide solution is 0.1 moles per liter. Any questions? Now this other one, this was also made by adding 100 grams to 250 mils. Is it the same concentration? Question. Mm-hmm. Yeah. What did I do? I don't know what I did. Yeah. 2.5 divided by 0.25 equals 10. I don't know what I did, but thank you. Obviously, I did something wrong. Let's back up. Do you wish you could do that sometimes in life? I sure do. Okay. 10.00 moles per liter, or 10.00 capital M. So this is 10 molar. Is the other solution 10 molar? No. Because KCl has a different molar mass than sodium hydroxide. It's the same mass that we put in, but the number of moles will be different. Where are we going to put this? So I don't know. Let's make it red. Just because. So KCl, we need the molar mass of that, right? KCl, potassium is 39.10 and chlorine is 35.45. 39.10 plus 35.45. 74.55. 1 mole of KCl is 74.55 grams. So we're going to do a real similar calculation to this one. 100 grams of KCl, and then we're going to use the molar mass of the KCl. I know what I'll do. We'll get rid of all these words that we don't need to see anymore. Then we can just write in there. So 100 grams of KCl, we have to convert that to moles. So we multiply by moles, divide by grams. Grams cancel out. We just calculated the molar mass, 74.55. So 100 divided by 74.55 equals 1.341 moles of KCl. So the molarity is going to equal the number of moles, 1.341 moles, divided by, what's the volume? 0.25 liters, 0.2500 liters. Let's see if I can do this one correctly. Divided by 0.25. 5.366 moles per liter, which is the same as 5.366 capital M. It is very important to recognize that the capital M means moles per liter, because chemists use them interchangeably, and so we'll see them used in the problems, in lab, on exams, all over the place. Any questions? So this particular exercise was asking for two different answers. That's not exactly 5, but it's close. So, pardon me? You think the math is a little off? That's entirely possible. I seem to be a little off today. 1.341 divided by 0.25. So if you did it like I showed it here, what I did is I had the full number in my calculator, and I didn't erase it and type it back in, and so it rounded to the 6. That doesn't work so good. If you do 1.341, then you come up with 364. Is that what you came up with? Now, is that a big deal? No, because it's in the last significant figure where there is uncertainty. Question?
You have the correct answer up to like the hundreds or thousands place. Is that going to matter when it comes on to the test?
On a test, the difference between correct answers and incorrect answers is generally significantly larger than what the last significant digit is. Because remember, in any number, there's uncertainty in that last digit. So like I did that calculation and I came up with 5.366. And that's because I didn't round as I was going along. If you did round, then you come up with 5.364. So what might be possible answers on the test? Well, they might have 10.00 and 5.364 and 0.100 and I don't know, 0.0043 or some. So if you're choosing out of these choices, even though your answer didn't come out, like if you got this answer, didn't come out exactly, this is obviously the closest one. So if it just differs in the last digit, don't worry about it. And like I said, we're not getting hung up on sig figs. We're practicing using them. And so, maybe you're completely ignoring significant figures in this problem, and you come up with some long string, but you see that it's here, this one has a last digit, and it's the same, where am I pointing? It's the same here, 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 and there it's different. That's okay. So if it's really close to what your number comes out to, that's good. Does that help? Anybody else have any questions? This is more of a concept question than an exercise. So we have two HCl solutions, A and B. Solution A has a greater concentration than solution B, and we're asked to say which of the following statements are true. So sometimes it's helpful to draw pictures. So here's solution A, and here's solution B. And it says that A has a greater concentration than B. Well, how about if we just make up some numbers? What if we say this one is 5 molar and this one is 1 molar? Just to give us something to think about. Let's look at these statements one at a time. If you have equal volumes of both solutions, solution B must contain more moles of HCl. Is that true? Well, what if we had 1 mole of this solution? I'm sorry, 1 liter. It's asking for equal volumes. If we have 1 liter of this, how many moles do we have? It's 5 moles per liter. There'd be 5 moles, right? And in this one we just said, for instance, this is 1 mole per liter. If we have 1 liter of the solution, how many moles do we have? 1. So does this one have more moles than the other or less? It has less, right? So then this statement A is not correct. Does that make sense? So there's no numbers in this problem. But you can make up some numbers. Make up easy numbers. You can make up some numbers for what if, just to see if the comparisons are true. Let's look at this one. If you have equal moles of HCl in both solutions, solution B must have a greater volume. Well, how could we make a 5 molar solution? We could put 5 moles in 1 liter, right? That's what 5 molar means. So 5 moles in 1 liter. This is saying if you have equal moles. So they're saying that this container also has 5 moles. If the concentration is less than this one, how could that be true? The volume must be larger, right? Because if we took 5 moles and we wanted to have 1 mole per liter, we'd have to divide this by 5 liters, right? And then we get 1 mole per liter. So this one is true then. And I'm not going to ask you questions like this on an exam, but I think it's helpful to think about them in lecture. If we want to get equal concentrations of both solutions, you need to add a certain amount of water to solution B. Will adding more water to this make the concentration go up? No. Because when we're adding water, remember, 1 molar is 1 mole per liter. When we're adding water to that, we're increasing the volume. That means we're dividing by a larger number. That makes the concentration go down. Think about concentrated orange juice, right? That can of orange juice, and you squish it to get it to come out of the little can. And then what do? You add water, right? Does adding water make it more concentrated? No, it makes it more dilute. It lowers the concentration. Because as it is, it's too concentrated and you can't drink that. So is this statement true then? No, not true. If we add, it says adding more moles of HCl to both solutions will make them less concentrated. Is that true? No. Because in that situation, we're adding moles, keeping the volumes the same. That's going to make them more concentrated.